Okay, hello everyone. I'm Huan Zhao from Hong Kong University of Science and Technology, and thanks for your interest in our work, metagraph-based recommendation fusion over heterogeneous information network. We can start. As we know, recommender system has become very popular in recent years, and here I will show you some examples. And here we have the product recommendation from Amazon. And we also have the question and answer recommendation in Quora. And here we also have the restaurant recommendation. And in one word, recommender systems are everywhere nowadays, which aims at providing items to people based on their interest. And in reality, they are not only useful for people, but also create huge revenues for companies. And in the literature, the most popular method for recommender system is collaborative filtering, which try to recommend items based on users' past behaviors. And it can be roughly categorized into the following types. Like the first one is user-based collaborative filtering, which try to recommend based on users who share similar preference, say, giving the same rating to items. Second one is item-based collaborative filtering, and which try to recommend based on similar items. Third one is the metric factorization, also known as the model-based collaborative filtering. The most popular one, which assumes that user preferences are controlled by a small number of vectors. Thus, the rating matrix constructed by user and items can be factorized into two smaller matrices representing the latent features of users and items respectively. And to obtain these two matrices, we need to solve the following optimization problem, which can be solved in gradient descent method. And due to the success of metric factorization in collaborative filtering, there are problems facing it. The first one is the sparsity of the rating matrix. I say in reality, more than 99% entries in the rating matrix are missing. The second one is the cost start. That is, some users, say a new user or new items, have no ratings. And both of these two problems impair the performance of rating prediction, collaborative filtering, and recommendation performance. And more importantly, metric factorization actually is not applicable for nowadays recommender system because the rating matrix actually is not sufficient for now much other extra information, also called side information in literature. Let me show you an example. And here we have a web page in Yelp for a very famous restaurant, Royal House, located in New Orleans. And here we can see from this web page, apart from the rating information, we have quite much other site information which cannot be modeled in the rating matrix. Like we have here is the location, and we have also the images. This is the review text, and we also have this is some metadata. Actually, all of these are very important vectors when we recommend a restaurant to people. And therefore, when we design recommending strategies, it will be not enough only considering, say, like users, items, and ratings. And actually, it should be a heterogeneous information network. And heterogeneous information network, we call it HINI in short, and actually can be represented by a graph where the nodes can represent different entities of different types, and edges represent relations of different types. And this is a small hint extracted from previous web page. And we can see here, we have entities of different types, like we have users, restaurant, Royal House, and a review, and we also have relations of different types, like the check-in, rate, mention, and so on. And then, based on this heterogeneous information network, we can define some network schema, which defines the relations between different entity types. For example, here we have a network schema, and here the A represents the aspects of the review text, and R review means review, and U user, B is business or item in recommender system, and CAT means category of item, and CI means city. And this relation we can read from this schema that user can check in business, and business belong to some category, and users can write the reviews, and in the review text they can mention some aspects like the price, food, service, and the review can also give ratings to a business. Okay, and this we have different kinds of relations. And then based on this network schema, we can make use of meta paths. Okay, here, a sequence nodes of entity types connected by relations and to recommend. In fact, many traditional recommending strategies can be modeled by multiple meta paths. Okay, here, actually, is user-based collaborative filtering. Actually, we recommend by similar users who check in the same business. And here, this actually is the social recommendation. We recommend based on what your friends check in. And this one, two businesses belong to the same category. Okay, we recommend by this information. Actually, it's very similar to the content-based recommendation. And in practice, actually, we can design many other recommending strategies by multiple meta paths. And in the meta path-based recommender system, actually, similarity between users and item is a key vector. And by one meta path, actually, we can define one kind of similarity. And after we obtain multiple meta path-based similarity, we need to utilize them all to recommend. In the literature, there are two works on this problem. And the first one is try to learn embeddings of users and items from multiple meta path-based similarity, which are then used in a linear model for the final recommendation. Second, they use the meta path to compute similarity between users, and then the ratings are predicted by similar users, very similar to user-based collaborative filtering. And both of these two works have demonstrated the effectiveness of meta path-based recommender system for the rich set information in ordered recommender system. However, there are also problems facing the meta path-based recommender system. Again, let me show you some example. Here we have two meta paths representing two recommending strategies. The first one we can say is user write a review and a review giving rating to the same business. Okay, we recommend by similar reviews giving rating to the same business. Second one is the review mentioned the same aspects. That is, the text information is very similar. We recommend by similar reviews in this sense. But the problem is that what if here the two reviews mention the same aspect, and give the same ratings for the same business? In other words, that this aspect of the two reviews are for the same business, and in this way, actually, we obtain a very complex structure like this. It's very common in nowadays recommender system that we say two users give rating to a business, and both write reviews to a business, and both of the reviews give the same ratings, say 5, to the business, and at the same time, the text of the reviews mention the same aspect of the business, say the price or service, something like this. And actually, this cannot be captured by meta paths, and therefore, our work is motivated by this problem. And generally speaking, we explore three things for recommendation on heterogeneous information network. The first one is we use a meta graph, a more complex structure instead of meta path to recommend. Second, we adopt a more powerful prediction model. It's the visualization plus factorization machine, which is much more effective than previous meta path-based recommender system. Third one, actually, we design method to automatically select important meta graph. Let's see the first aspect. Here, we give a basic introduction of meta graph on heterogeneous information network. And a meta graph is a directed acyclic graph with a single source node and a single sink node. It's evident that these two nodes actually represent the user and item respectively. And in fact, we can see that metapath actually is a special case of metagraph. Or in other words, actually, metagraph is more generous than metapath in terms of measuring the similarity between two entities. And in previous and here and for the metagraph-based recommender system, similarity is also the key vector. And here in this work, we use the number of instances of a metagraph connecting two entities as the similarity between them. And in this slide, I will show you by example, this similarity can be computed in a simple matrix computation. And here, actually, we first obtain the CP1 by dot product of WRB and its transpose, and then CP2 by WRA and its transpose. And here, each matrix represents the number of instances of structure connecting two entities. For example, each entry in WRB represents the frequency of a review giving rating to a business, and each entry in CP2, the second one, represents the number of frequency of two reviews mention the same aspects. And then CSR, the number of instances of this special structure connecting two reviews can be obtained by element-wide product of CP1 and CP2. Finally, we can obtain CM by a dot product of sequential matrix representing the number of instances of this metagraph connecting user and items, namely the similarity between user and item based on this metagraph. Okay, and after we obtain multiple metagraph-based similarity, and it is also challenging to assemble all this metagraph-based similarity. In previous metapath-based recommender system, they use a linear model for the metapath-based similarity. However, in this work, we argued that the nonlinear interaction among different metagraphs also needed to be considered. And to achieve this, we adopt the factorization machine for two reasons. The first one, it can capture nonlinear interactions among different features. The second one is that its good ability of prediction in recommending scenarios. Okay, here, the equation of factorization machine is given here. Y is the predicted ratings, W and V are the parameters, and X is the feature vector. And here, actually, W is to capture the linear interaction. Actually, it's the part of a linear model. And V is to capture the nonlinear interaction among features. In practice, we usually focus on the second-order interactions. Okay, now I will introduce you how we incorporate the metagraph-based similarity into factorization machine. Actually, we adopt a MF plus FM framework. That is, we first factorize each metagraph similarity matrix between user and items into two smaller matrices. Then we get the latent features of user and items from this metagraph. And then we concatenate all the latent features from multiple metagraphs as one feature vector, which are finally fed on to the factorization machine. And in this way, all the metagraph-based similarities can be utilized more effectively. Okay, I will introduce the method to select the metagraph. Technically speaking, we add two regularization terms to the objective function called the L21 norms, which can select parameters in groups. That's why it's also called group Nassau. And here, one group corresponds to one metagraph-based latent features. And then finally, the objective function becomes the non-convex, non-smooth optimization problem, which can be solved by NMAPG algorithm proposed in 2015. Okay, that's all for the technical parts of our framework. And next, I will show you some experimental results to demonstrate the effectiveness of our framework. And here, the data sets are introduced first. We use 4 datasets in total, and the first two are two well-known recommending datasets, the Yelp and Amazon. And here we can see from this table that we have so many kinds of set information here. And another two datasets are provided by one previous work we denoted as the CIChem Yelp and CIChem Douban, also a very popular recommending dataset. And we also show the density of all the datasets computed in this way. And below, and we can see here, actually that it's quite sparse for all the 4 datasets. And in terms of the performance evaluation, we use the RMSE metric, which measures how good we recover the rating matrix. And usually smaller value means better performance. Okay, now we show the performance of comparing to other business. And here, our model is called FMG. Okay, FM with group not so here. And from this table, I want to emphasize 3 things. Observation. First one is that FMG consistently beats all baselines on all data sets, both the traditional recommender system, the metricalization, and the factorization machine for ratings, also the metapath-based recommender system. And with this demonstrates the effectiveness of our framework. And second, okay, comparing to the SumRack, okay, we use the dataset it provided and as well as the same metapath it uses in its experiment. And we can see here, FMG also beats SumRack. Actually, this can demonstrate the effectiveness of the adoption of factorization machine. Or we can see that it's effective to capture the nonlinear interactions among the different metapath features. Okay. Third, actually, in the 2 metapath-based recommender system, SumRack outperformed Heterogeneous, and actually mainly because that it uses metapath in style like the user star user business, while Heterogeneous uses metapath in style like user business star business. And interesting is that the result of our metagraph selection method also shows that metagraph in style like the user star user business is more important than metagraph in style like user business star business. And then next I will show you the result of our metagraph selection result. We show Yelp first. Here on the left bottom, we show all the 9 metagraphs we used in the experiments, and on the right, actually, we show the RMSEs of each single metagraph comparing to all. Actually, we can see here, the performance of using all metagraph in our framework is the best. And on the upper side, we list all the selected metagraph-based features in the table. And we can see here, most of the selected metagraphs are in style like the user star user business, and very similar to those in SumRack. This can also help to explain why SumRack outperforms Heterogeneous in terms of RMSE. And okay, this is the result of selected metagraph for Amazon, very similar to Yelp. We also show the RMSEs of each single metagraph compared to all, and again, the performance of using all metagraph is the best. And another observation is similar to the result in Yelp, that the metagraph in style user star user business are preferred. Okay, now we show the scalability of our algorithm. And from the figure, we can see that our algorithm, the cost sum is linear to the number of ratings, and that means our method can easily to be applied to large data set. And okay, finally, I summarize our work in the following. The first one is actually we are the first one to use metagraph on heterogeneous information network to unify rich set information for nowadays recommender system. Second one is we design or we adopt the MF plus FM framework to more effectively assemble all the metagraph-based features. And third, group nav saw is used to select important metagraphs. And finally, actually, in this paper, we show or we demonstrate that heterogeneous information network is a powerful tool for nowadays recommender system where rich set information are available. Okay, that's all. Thank you.